Hello everyone and welcome to today's WorkSafe Tasmania Month webinar. I'm Stephanie from WorkSafe Tasmania. Before we start, please take a moment to read the following slide about information received today. To interact in today's webinar, please use your control panel to type and submit questions for today's presenter. Questions will be answered throughout today's webinar. Today's webinar is also being recorded and only presenter and moderator webcams will be used. It is now my pleasure to introduce today's presenter, Simon Sharp, Contractor to the Institute of Quarrying Australia. Simon is a certified occupational hygienist and a registered nurse. He has over 25 years experience in occupational health and hygiene in heavy industry, mining and processing facilities. He has taught students for the Australian Institute of Occupational Hygienists, AIOH, Occupational Hygiene Training Association, OHTA, and the British Occupational Hygiene Society, BOHS. In recent times, Simon has been the Occupational Health and Hygiene Regional Manager for Newmont Mining and team leader of a hygiene team for a major consultancy. Simon is currently a Principal Hygienist and Technical Training Specialist for Red OHMS Group. His qualifications include a postgraduate certificate in Disaster Risk Reduction and Sustainability, postgraduate certificate in occupational hygiene, a postgraduate certificate in occupational health and safety management, and a Bachelor of Science in Nursing. Welcome, Simon.
Okay, thanks, Stephanie. So, what we're going to be covering today, we're looking at an introduction to respirable crystalline silica, where what we're hoping to cover really is what is respirable crystalline silica, how does it affect the body, and the way that we manage it, and what are work exposure standards. So there's a few things on the slide there that we're going to be covering today. Now I have control, is that correct, Stephanie?
Correct.
Righto, let's go. So, here we go. So, here we go. Introduction to respirable crystalline silica. There's just a slide there with some respirable. It's not respirable, but it's crystalline silica. So if we go further on, let's have a look. So dust, what is this dust idea? So dust, really, some dusts can cause minimal health effects, but can still cause irritation and aggravate pre-existing respiratory problems. So some dusts can be toxic, depending on its source material, such as respirable crystalline silica, for example. Lead, other heavy metals can also have toxic effects. So the size of the particle is what we're looking at, and the size actually matters quite a lot. And we talk in hygiene terms that there are two main classes of dust particles. We talk about inhalable size dust and respirable size dust. So if we have a look at this, here we go. So particle size, sorry, it's a bit touchy, the slide. So inhalable dust. Inhalable dust is all of the dust size. So when you're in a dust cloud, everything you can see and the size of the particles that you can't see as well. So inhalable dust is the total amount of dust that can be inhaled. We inhale about 50% of those dust particles greater than 100 microns or micrometers. Large size particles are predominantly filtered out by the nose hairs. The smaller particles obviously are the ones that tend to bypass all the protective mechanisms in a human body, and they can penetrate much more deeply into the lungs, and are the ones that we're most concerned about. The larger particles usually are coughed up, spat out, or just swallowed. And you can see in comparison to a human hair, we're looking at fine beach sand at about 90 microns, and the size that we're really concerned about is the size that's less than 10 microns. Okay, so respirable dust, similar picture on the right hand side, but respirable dust is the size of the dust particles that are less than that 10 microns, as I suggested. They're inhaled very deeply into the lung the lung fields, and they can actually get right down to the gas exchange area of the lungs. So that's where, in your bunch of grapes or your alveoli, that's where the air exchange happens. So that size of the particles is respirable. The particles are normally too fine to actually see unless there's actually very specific lighting conditions. So dust that you can see is not necessarily the respirable size dust. So we're concerned about the size of the particles that you can't actually see. Now, crystalline silica is one of the most abundant natural materials that makes up a major component of most rocks and soils. It actually occurs in a crystalline form or a non-crystalline form, and the non-crystalline form is called amorphous form. We're most concerned about the crystalline form, and you can see down in through the slides there, we've got electron microscopy of materials down to that 100 micron size, and you can see that there's lots of crystals, if you like, in through the material in through there on both of these sides of the slide, sorry. So that's the component that we're actually really worried about. Very touchy, these slides. So if we're looking at materials that might have crystalline silica in it, we're looking at up to 40%. You can have within granite, shale can be 22%. Natural sandstone is really quite significant. So those people working with natural sandstone can be exposed to up to 67% crystalline silica within that particular material, and engineered stone can be thereabouts 90% plus of crystalline silica. And obviously different types of rocks and products can have different amounts of silica within it. Now we've got a picture on this right hand side there of a human hair and silica dust, which is actually attached to that silica, to that facial hair. Now you can see that the size of the particles we're looking at are very much smaller than the width of a hair. Now that comes into play a little bit later on when we talk about respiratory protection, and the fact that unless you have a very clean and good seal around your respiratory protection, so your masks, then obviously the silica dust can actually get in under the seal and you can still breathe it in. So obviously the respirable crystalline silica, the slide talks about the idea of it. It's quite aggressive and it can cause quite a significant amount of lung damage because it can penetrate so deeply into those lung fields. And obviously, if you're exposed to enough of it, it can cause some lung disease. We'll talk about that in a moment. So we talk about RCS, so that's respirable or respirable crystalline silica. So RCS is classified as a Category 1A carcinogen by the IARC, and that's the International Agency for Research on Cancer. Respirable crystalline silica dust is created obviously when crystalline silica is broken down and then it's released in the air. So there needs to be some form of mechanical crushing action going on for that size particle to be created. And that can happen very often with drilling, blasting, lots of mining activities like excavating, grading, loading, transporting, crushing, cutting in manufactured stone, for example. Breathing in the respirable crystalline silica dust can damage people's lungs and lead to serious diseases, including silicosis and lung cancers. So, with regard to crystalline silica, sites need to understand the materials that they're actually quarrying or they're processing. So we're not just talking about mining, we're also talking about other activities such as people who might be working with manufactured stone or stained masonry activities as well. What you need to understand is the percentage of crystalline silica that you're actually handling, and if it's a made product and an SDS is available, that should give you an indication of what the percentage crystalline silica is for that product. If the concentration is greater or equal to 0.1%, then it's actually classified in Australia as a carcinogen. We can be caught out sometimes with imported products because different countries may have a different percentage of silica before they call it a carcinogen. But in Australia, it's 0.1%. So you should know also any other hazardous materials that might be within that material as well if you're handling it. So obviously heavy metals like lead, arsenic, and cadmium, and a few of those others. So we've just got a slide in here. This is data from the Queensland sector. Excludes coal mining in through there, and it talks about people's personal exposures. So that's how much dust containing respirable silica, crystalline silica that people might be exposed to over the recommended level. The recommended level is called the exposure standard, and we'll come to that in a moment. So you can see that throughout within quarrying and surface, it's remained thereabouts fairly equal across the way. So the exceedances have gone from thereabouts 2.1% exceedances for the number of people who were actually monitored and had some sampling done, right up to thereabouts 8.3% of the exceedances. Now the exceedances could be because there's more people working in the industry, or more monitoring being done, or it could be other factors like inappropriate or ineffective controls actually being in place for people to be exposed to that particular contaminant of respirable crystalline silica.
A question has come through, Simon. How would you work out the percentage, for instance, someone cutting concrete or slab?
It depends on the product. If you have a product that has been manufactured, then all products must have an SDS by law. The Australian in the Australian realm. So if you're working with a product that has been manufactured like cement, for example, you would have within that cement bag or the cement product, the manufacturer must give you an SDS for that product. Otherwise, you can take a sample of that material and send it off for analysis to the lab. I hope that answers the question there. It can be, sometimes you've got a pretty good idea and you can go with that. And based on that understanding, is there likely to be a reasonable amount or not, then you would put appropriate controls in place, regardless of whether it's 2%, 6%, 90%, makes no difference. In the end, you need to use some form of respiratory protection and other types of controls. Okay, so what we have in through here is some more Queensland data, just a slide on through there. You're looking at the different types of roles, if you like, for people who might be exposed to crystalline silica in Queensland. And within here, we're talking about support and maintenance activities. Very often they are guys or women, obviously, who might be working in the maintenance area for machinery, and they can get exposed more so than sometimes the people actually doing the work. So open cut, drill and blasting, that's only 3.5 thereabouts % of exceedances, where the maintenance guys in the workshops might be exposed to much more than that, up to 10.6 thereabout %. And those figures haven't really changed since thereabouts 2017. Okay, so let's go into a little bit more guts. So lung anatomy. So how does this actually, how does it work? So how does your body go about protecting itself? First of all, we need to understand, how does the lungs work? How does how do you get this air in? How do you get it out? How does oxygen get transferred into your bloodstream? Because that's the important bit. So realistically, what we've got is most people know they've got a lung. In fact, most people might even know they've got two. But what happens is, obviously, you breathe air in through your upper airway. It goes down in through your trachea, and then branches off into your bronchi, left and right, and then into the lung fields of your left and your right lungs. And it goes obviously branching down smaller and smaller and smaller until you get to the very bottom end, or the terminal end of your airways, which is your alveoli. And that's your bunch of grapes, if you like, if you're familiar with that. The air exchange and gas exchange actually happens at the bunch of grapes. So that's in the alveoli. There's a little bit of trivial information in through there. Each alveoli is thereabouts 0.1 millimeters in diameter. There's lots of them. There are about 300 million of them, and they have a huge surface area to allow for that gaseous exchange. They're about the size of a tennis court, and you breathe in thereabouts 9,000 litres of air. So there's 9,000 litres of air which would otherwise naturally be protected by various mechanisms to allow you to get the oxygen exchange down in the bottom of your bunch of grapes. And we'll come into those protective mechanisms in a minute. So this is just a quick picture of a representation of down in the alveoli, so those bunch of grapes. So if you look at air comes in, you have gaseous exchange with your oxygen transferring across from your lung fields into the very small venules and arterioles, so that they're just very small size blood vessels, so you can get the oxygen transfer and the carbon dioxide transfer as well. There is a bit of water in there too. The way that this works is that the cell walls are very, very thin, so you're only looking at, I like to put it into context like there's one or two sort of layers of cells, and that's it, and that allows the gases to be exchanged across the membrane. Now, if you get some abrasions in through there, a little bit like when you get a new pair of shoes, you get a bit of a blister forming, and then it goes and gets hardened, and you get a callus forming. Then within those, same sort of idea within your alveoli at that gas exchange level, rather than having the two cells together and the oxygen and gases can exchange quite easily across those the cell membrane. If you've got a bunch of cells all together, which is now a callus within your lung fields, within your alveoli, it means it's much harder for the gases to be exchanged across that membrane. And it also means that it's not so lovely and what we could say compliant. So that means it doesn't stretch so well, so it doesn't allow the oxygen or the air to come into the alveoli and then get back out again, because it's very, very tightly bound now, because it's all hardened up like a callus. And that's where we talk about fibrosis in the lungs. Okay, so the body's defense mechanisms, these are the things I was talking about that would normally protect you. These are things that are in place for the normal human being long before we decided to put ourselves in dusty environments so we can earn some money. So after dust is inhaled, most of it is removed by 5 different methods. There's 4 just in through this little section. The next slide will come up with the other one. So as I suggested, these mechanisms have evolved over time to defend ourselves against natural airborne dust and other contaminants. But of course, we go and put ourselves in unnatural environments so we can earn money and turn a dollar. So therefore, we need to be mindful that very often our normal body defenses can be actually overwhelmed. So if we talk about from the top down through to the bottom, our protective mechanisms. So the first one is in through your nose. So there's nose hairs up in through there. That's the first defense mechanism. So the nose hairs will be able to help to filter and trap the larger size particles. So the larger size particles get sort of stuck up in through the nose and the back of the throat sort of area in through there. Going down through the respiratory system in through there, you've also got what they call cilia. Cilia are little hair-like structures on the airway walls, and what those little hair-like structures do is they tend to trap any larger size particles as well. Within that, there is also a mucus blanket, and that mucus blanket also makes those particles stick in through there. And there is another thing called the cough reflex. So further down in through your lungs, or your airway, sorry, at what they call the hilum, which is that bifurcation in through there where the airway actually splits into the left and right. Down in that section in through there is where, again, the larger size particles irritate enough so that you can cough them out. They talk about the mucociliary escalator. So the mucociliary escalator is just where the mucus blankets and the cilia work together to brush upwards so that you can cough up any contaminants. And that's in the upper airways. Now, we're left with the bottom part of your lungs, the important bit, I suppose, down in through the alveoli or down to that level. And that's where, or actually, sorry, we'll cover this slide very quickly. Dust removal by the upper respiratory section. So particles are cleared out mostly via that mucociliary escalator. It traps the particles and carries them up out of the lungs. So there's two parts to it, as I suggested, is that mucus layer, or the gel layer, and the cilia, which is those little hairy-like cells. And as I suggested, that mucociliary escalator system does not extend right down to the bottom part of your lungs into the small parts of the alveoli, or those bunch of grapes.
Question is, sorry,
go on.
Simon, a question has come through. If you're handling, shoveling, sweeping silica sand with minimum sieve size of 75 microns at 0 to 2% total amount, is there a need to be concerned with inhalation?
I'm going to say yes. It obviously depends on how much you're being exposed to, but if you're doing dry shoveling or sweeping, then you're more likely to make it airborne. Yes, the size that you're talking about, remember, we're talking about size fraction of less than, if I've got this question right, less than 10 microns is obviously the size that we're really most specifically worried about. And if the size of the particles are larger than that, then it's less likely to be an issue, because those size particles tend to get scrubbed out long before they get down to the bottom parts of your lungs, down into your alveoli. So I think there's two parts there. One is that sand, or is that material less than 10 microns? And if it is, then it's definitely more likely to be airborne, and the size that is likely to cause issues down in through your lung fields. And if it's larger than the 10 microns, then less likely for it to be entrained in the air long enough for you to actually inhale it in the first place. But remembering it, if the material is not homogeneous, so it's not all the same size, then you can't be confident that all of it is going to be greater than that 10 microns, for example. And I hope that covers the question.
Thanks.
Okay, so we're now down to the mechanisms that the body has in place for dust removal or management of airborne contaminants down in the lower respiratory system. So that's where you don't have those cilia anymore, and you don't have the cough reflex, you don't have the mucociliary blanket going on. Down through there, we're left with our last form of defense, which is our macrophages. So that's our white blood cells. And what they do is they try to engulf and destroy the contaminant that's gone down that far into your lung fields. So what happens from there is it can either be digested by those macrophages and then removed by the lymphatic system or the venous system, or potentially you might be able to cough it up if there's enough irritation and there's enough enough of it to be able to cause some mucus that can be coughed up into that upper airway, and then you can cough it out. Now, something really important to understand is with the case for the respirable crystalline silica is that the macrophages are unable to process it. So that means that the respirable crystalline silica, most specifically, the macrophages cannot engulf it appropriately, and they cannot digest it and change it into something else which the body can actually go and remove by way of digestive sort of systems via your lymphatic or your venous system, or your blood system. So that means that it stays there. A little bit like asbestos. Asbestos fibres, your macrophages, so your white blood cells, are unable to process it. They're unable to digest it to be able to get rid of it. So what happens from there is with respirable crystalline silica and asbestos fibres too, of the right size, is that it just causes fibrosis. So remember that irritation idea when you get a new pair of boots. It just irritates, and then you get dead macrophages which have come in to try and process that material, which then causes further fibrosis and irritation. Okay, so this is what we're talking about in through here. So what we're looking at is we're specifically looking at silica. So silica dust inhaled in through the alveoli. So that's one of those terminal bunch of grapes. Here we go, in through there. and as I suggested, it's 1 or 2 cell thick only. You've got silica particles in through here, and the macrophages, which are the white blood cells, are busy trying to engulf them and process them and dissolve them, so that you can get rid of them. Now, what happens in through here is somehow it just happens to be that silica is poisonous, if you like, to your white blood cells or your macrophages, so they're unable to dissolve it or change it into a different form that your body can process. So the macrophage or the white blood cell disintegrates and then causes some more fibrous tissue. They're called fibroblasts, but regardless, so fibrous tissue is formed, and then you get enough of it in that alveoli that you end up with a dense nodular scar tissue, and then you can see quite easily in through this representation that you don't get any air exchange in through there, because it's the tissue is the wrong type of tissue to allow for gaseous exchange. So you don't get the air exchange, and you don't get that compliance or that stretchability of your alveoli anymore. So that's the process that goes on. So health effects. So exposure to silica, there are a couple of surprising things, and it's not only inhaled to you specifically for your lungs, but let's have a little bit of a look. So what we have a picture in there is just some people working in an industrial environment. It's a manufactured scene, obviously, and we're looking at people working, doing chasing or cutting of concrete. So health effects. So the workers exposed to elevated levels of RCS, remember that's respirable crystalline silica, they've got an increased risk of developing lung diseases like chronic obstructive pulmonary disease, or COPD, chronic bronchitis and emphysema, silicosis of the 3 forms that we'll cover in a second, and progressive massive fibrosis. So there's a few things in through there. Here we go. However, there's some other things that go on as well. Obviously, the lung cancers is one of them, so we're looking at lung-specific issues, but there can also be some kidney damage, and that's due to the nano-sized particles. So that's the very, very finest particles that can actually make some form of exchange across the alveoli into your bloodstream, and then they can cause some damage distal to your lungs and through your kidneys as part of the process of elimination. And scleroderma is another disease associated with silica exposures as well, and that's an autoimmune type of reaction. So your body starts to attack itself, and it attacks the connective tissue. So that is your tendons usually, and results in the formation of scar tissue actually within the skin itself. Sometimes so you've got quite a tight skin which forms contractures. So contractures is where your body or your joints then go into a tight sort of formation. You can't stretch them out. So you can get that with your skin joints and other potentially other organs within your body as well. So the health effects are really dependent upon the type and of the concentration, and the duration of the exposure. So particle size, composition, concentration, duration, they're all the things that we look at when it comes to the likelihood of having health effects. And disappointingly, those diseases might not be apparent for many years after the exposure has actually occurred, and possibly a long time after any continued exposure as well. So you may have actually finished or ceased any further exposure, yet the disease process continues on. So a quick look at chronic obstructive pulmonary disease, they're collectively known as COPD. It's the most progressive types of lung diseases, and the most common ones are emphysema and chronic bronchitis. So emphysema is when the lining of those bunch of grapes, so your alveoli, become non-compliant, so they don't stretch anymore, and that's due to fibrosing activities going on within there. And then you've got chronic bronchitis. Bronchitis is on the right-hand side of the slide. If you have a look, a normal airway should be nice and pink, nice and open, without much mucus going on. Whereas chronic bronchitis is where you have an inflammation reaction going on within your airway. It causes a restriction in the lumen, so the restriction in the area that air can pass through, and it also causes mucus to be produced as well. So you get that chronic, what they call smoker's cough going on. Other health hazards to do with silica exposure could be silicosis. It's incurable at the moment. It's a lung disease caused by the inhalation of respirable crystalline silica. It's a result of the body's response to the presence of that RCS in the alveoli. We've already covered that concept. There's three major types or forms, if you like, of silicosis, and that's acute, which happens very, very quickly. Chronic, which happens over a long period of time, and then accelerated, which means that it happens quickly after a period of latency or chronic symptoms, and then suddenly it starts getting much more symptomatic. And there's just some X-rays in through there. What we're looking at within normal healthy lung fields in an X-ray is it should be nice and black. Lots of air is able to get in there, and that's the black bit, if you like, and then you start getting fluffy, cloudy shadows, is what they call it, of white stuff, which means that the X-rays can't pass through the lung fields, and it's because it's all fibrosed up with other tissue, which is not air. Right, so acute silicosis. The time of onset for acute silicosis varies from disappointingly a few weeks to thereabouts 10 years after the start of exposure. Normally it happens within the first 1 to 5 years. Acute silicosis frequency results in death due to respiratory failure because of the activities within your lungs, which compound to make sure that your lung fields become affected, fibrosed, don't allow for the oxygen exchange anymore. Acute silicosis progresses in the absence of any further exposure to respirable crystalline silica. As I suggested, you might be exposed to the RCS and then change jobs or have better respiratory protection or other controls in place, don't have any further exposure to RCS, but then you can still have the silicosis progressing. Chronic silicosis, that's the most common form. It's not quite so spectacular, so you don't tend to hear about this quite so much in the media as you do for that acute onset. However, the time for onset for acute silicosis varies from 10 to 20 odd years. There's a long time after your initial exposure potentially, but that can be due to relatively low levels of respirable crystalline silica dust exposure. The chronic silicosis process, again, you might have been exposed ages ago and then no further, and yet the silicosis can still progress. Now, the accelerated silicosis is where, I'm just looking at the time, okay, with intense exposure to respirable crystalline silica, and it rapidly progresses after a period of time. So it develops after 5 to 10 years thereabouts from the start of the exposure, and typically associated with more moderate exposure as opposed to the lower exposure that you might get for potentially chronic silicosis. The symptoms are very similar to chronic silicosis, and again, the accelerated silicosis, it progresses in the absence of any further exposure to silica. So symptoms of silicosis. Normally those symptoms appear many years later, but sometimes it can be, like as it suggests, a few months after your exposure. The symptoms typically worsen over time as the scarring activity in your lungs continues. So early symptoms of silicosis are fairly innocuous. You don't think much of them necessarily. The first bit really is just a cough. And like a bronchitis type of cough, which is just an irritation of the lungs. As I suggested earlier, the lining of your lungs is irritated, it gets a bit swollen, you don't get so much air passing through, and there's an increased mucus production or phlegm production as well. So it's more of an irritation type of thing. But then you start to progress through the silicosis timeline, and then you start to get some chest pain along with that breathing difficulty. That's because the lungs are being fibrosed. They're not stretching as they should do to allow the air exchange to come in and out, and that's where you get your chest pain and that breathing difficulty. From there, you start losing, because you're not getting so much oxygen into your bloodstream, then you start to get fatigued, start to lose your appetite as well. So, apologies. As the disease progresses, of course, the breathing becomes much more difficult. The cough is very much more persistent, and the chest pain can increase quite significantly. You end up with the weight loss. You can have night sweats as well. And that chronic bronchitis-like symptoms occur where the lungs also have other sounds associated with it. So whistling, wheezes, crackles, all these other funny noises within your lungs that didn't used to be there. And that's to do with the increased mucus production and fibrosing as well. So obviously the airways are becoming smaller, and therefore the amount of air that you need to go, the time of a breath going in for the air to get in and do some air exchange has to go through narrower airways. So therefore it's more likely to whistle, or the mucus in there rattles away, and that's where you get those crackles and things as well.
A question, Simon. Would the phlegm
Yes.
production be relatively constant throughout the day?
Yes. It would be. You may, we tend to see in the health realm, the phlegm productions always seems to be more at night, and that's mostly because it's happening all the time, and you wake up and then coughing doesn't normally happen necessarily when you're asleep as such. You've got to be a little bit more conscious to be coughing, so you might notice it. So yes, it is more noticeable during the day. And you may wake up in the middle of the night and you have a coughing fit, and that's just because you haven't been awake during that period of time, and you've also been laying down flat. So that means that the mucus pools in your lung fields, and then it causes more irritation later on. So it's fairly constant. It's just in the middle of the night you might wake up and have a bit of a coughing fit, and you think, geez, I'm coughing more than I normally do during the day. It's really a function of you lying flat and your lungs they sort of fill up with the mucus which is being produced all of the time. Bit of a trick question, that one. So silicosis symptoms, as that scarring process continues, obviously you start to get those signs of the chronic lung disease. You can see some changes in the chest x-rays. You can see changes in your lung function tests as well, where you can't get that air in and out of your lungs in the same way that you used to. So obviously you increase your breathing rate because you still need the same amount of oxygen, but you can't get it, so you're busy trying to breathe a bit more, bit faster. And because you don't have the same amount of oxygen, you tend to get these bluish discoloration of the lips, which is hypoxia, big name for not enough oxygen. There is no cure for silicosis, therefore really prevention is the only option there. So the idea is don't get sick in the first place. And as a hygienist and a nurse, that's my prerogative. I always like the idea of don't get crook in the first place. So let's look at how we can put controls in place so you don't have that exposure. All right, and we'll move further into some other lung diseases. So another one called progressive massive fibrosis. So PMF, it is a known complication of silicosis and a progression of that chronic silicosis. And as we've already discussed, it can develop long after the exposure to crystalline silica has actually stopped. And we talk about nodular lung lesions becoming larger than thereabouts 1 to 2 centimetres. It's all academic, really. It just means that there's big bunches of fibrosis that you can see via an X-ray. And in through here, normal lung field, as I suggested before, should come up on an X-ray that's black because it's full of air, and that's what you want. And when it's not full of air and it's full of hard mucus or fibroses and things like that, that's where you get this white patchy bits and pieces in through there, and that should not be there. And this is a chest X-ray of PFM or PMF, sorry. Right, so lung cancers, depicted in through there, obviously this white sort of stuff in through there and around the bifurcation of the airway in through there shouldn't be there. So in cases of people diagnosed with silicosis, lung cancers can also develop. So lung cancers are different. Cancers are not just fibrosis. Cancers are where the types of tissue that is replicated when old cells die, the new cells are not the same, they don't form the same function as the previous cells. So cancers can be malignant or non-malignant. Non-malignant means that they just replicate themselves and they stay put. And the malignant cancers are the ones that spread further because within the DNA of the cell, they've forgotten to turn themselves off, so they replicate themselves uncontrollably. So that's in essence what a cancer is. It's cells where they shouldn't be doing functions that they shouldn't be doing in that area, and sometimes they can be replicating themselves too quickly. So that's where you get a mass formed. Okay, so we were saying earlier that respirable crystalline silica is classified as causing cancer to humans by the IARC guys. And there's a note in through there. Smokers have an increased risk of developing lung cancer when exposed to respirable crystalline silica at the same time. So this is due to what they call synergistic effects. So there are two different types of effects that we have when we're exposed to different types of chemicals. When we're talking about toxicology, one is an additive effect. So two chemicals or contaminants, the effect is equal to both of them just added together, if you like, as if they were taken separately as exposures, whereas synergistic means that the effect of the exposure to the two chemicals together is much greater than either of those chemicals by themselves. So that, for example, smokers exposed to respirable crystalline silica may well be not just twice as likely to get lung cancer, it would be more likely to be 10 times. Why is that? Not quite sure, except that obviously there's cancer-producing agents within cigarettes, and cigarette smoking irritates the whole lung pathway or the whole airway. So that means that there's more likelihood for there to be scarring going on, and it also gives the opportunity for the respirable crystalline silica to actually stick and cause some further damage because the lining of your lung is already irritated. All right, workplace exposure standards. So we've got guidance. There's just a picture of the Australian, the current Australian guidance for interpretation of workplace exposure standards for airborne contaminants. So that's produced by Safe Work Australia, and it's online free. It's a really good reference. Hygienists use this reference constantly. Oh, hang on. Let's go. There we go. There is also another book, form of guidance from Safe Work Australia. Again, it's only just come out at the beginning of October. So this one is the updated workplace exposure standards. So one is about the actual standards. Let me just go back very quickly. And the other one is the interpretation of those in standards. And they both of those documents work in tandem with each other. So let's go back here. So Safe Work Australia has just published that new exposure standards for airborne contaminants on the 1st of October this year. And there's been a revised exposure limit or workplace exposure standard for crystalline silica, and that is now at 0.05 milligrams per cubic metre. In the past, it was 0.1 milligrams per cubic metre. So what's happened is that current evidence has shown us that there's enough supportive evidence to form the risk profile for silica to say we need to actually halve that exposure limit to make sure that people are do not have adverse health effects. Okay, risk management. Let's go into there. Okay, so the way hygienists go about things is we like to identify the risk. We're going to be talking about specifically respirable crystalline silica here, but it applies to any chemical exposure that you might have. So site management needs to ensure that there's a process in place to identify any risk from respirable crystalline silica or any other contaminants at a workplace. This is a borrowed slide, so it says quarry, but any workplace. The identification and assessment of that risk should involve a cross-section of the actual workforce on the site with a wide range of knowledge and of the work processes and activities and experiences. The assessment should be based on what we call similar exposure groups, or SEGs, and the tasks that they are performing, and it should involve a competent person such as an occupational hygienist to do the risk assessment. So this is a health risk assessment we're talking about. We're going through here. So similar exposure groups. We use, as hygienists, similar exposure groups all the time to give us statistically relevant information. So SEGs are used to identify a group of workers who have similar exposure to risks. So they might work in similar areas, they might have similar tasks or frequencies, and they might be utilising or being exposed to similar materials and processes to complete various tasks. So typical workplace exposure groups that we might come across could be, for example, in quarrying, could be administration workers. They'd obviously have, as a group of workers, who have much less exposure than the maintenance personnel, like fitters, electricians, diesel mechanics, and they would all have slightly different exposures to materials, like the quarry supervisor and manager. They're usually about 50% in the office and 50% in the field. The blast crew will be in the field most of the time, and plant operators are busy being exposed all the time. So that's our similar exposure groups that we look at, and we look at them not in isolation. So the SEGs of various workers, as you can see, fitters, electricians, diesel mechanics, may form the maintenance similar exposure group. So we treat them all as equal types of exposures, and we'll do monitoring for those guys, and we can say that, let's say we're looking at sampling a fitter's exposure. We can say that the fitter's exposure is going to be the same as or similar enough to the diesel mechanic, so that we can get an understanding of a bunch or groups of people's exposures. Okay, so identifying that health risk. So the risk assessment should assess what type of materials might be present. Is it a chemical or airborne contaminant of some kind? What other minerals or metals might be present as well that could cause harm? So, is there arsenic in that particular material as well, or lead or zinc or what have you? Chemicals that might be used in the maintenance activity. So we need to check the SDS for those materials as well. We'll be looking at welding, fume, cleaning products, construction activities, cement dust, sandblasting, grit, and things like that. We'll be looking at so we've got chemical risks, and then we've got physical risks. So we'll be looking at health, heat, stress, sliding, manual handling, ergonomics, noise, whole body vibration, hand arm, radiation of various types, electromagnetic fields, and or UV. And then we've got other types of risks, like biological risks and psychosocial risks as well. Obviously, this particular slide pack and workshop is mostly focused on the respirable crystalline silica component. So, okay, we've identified the risk for this particular work group, and it's respirable crystalline silica exposure is one of those ones. So we've identified that risk. Fantastic. Now, what we need to do is understand exactly how much of that are people being exposed to. So this is where the exposure monitoring or sampling comes into play. And we've got, in this particular picture here, we've got a sampling pump. So what that does is brings air in via the sampler over a filter, which we send to the lab. And this tubing is just attached to that sampling pump. So that's like a vacuum pump. It just allows air to be drawn in across a filter, and we send that filter off to do analysis, and then we gain an understanding of exactly how much contaminant a particular person might be exposed to during the course of their work day. So we like to do personal air monitoring, which is very different from static air monitoring as hygienists. Static air monitoring is just where you poke a pump in the corner over somewhere and it just stays there all day. It's got nothing to do with someone's personal exposure, because people move around through the workforce and stick their heads and they're in various places. So we like to get an understanding of someone's personal exposures. So you're required to do air monitoring to determine the airborne concentration of that respirable crystalline silica at your workplace if you're not certain if you're exceeding the exposure standard, or monitoring is necessary to find out if there is a risk to health, or it could be you might be needing to do it, the monitoring as part of a legislative requirement. Certainly in Western Australia, we have legislative requirements. Sorry, what was I talking about in Australia? In Western Australia, we have legislative, local legislation that says that you need to do monitoring if the risk is present, certainly in the mining environment, and you need to upload those results as well to the regulator. That also happens in Queensland and I think New South Wales. Okay. So personal air monitoring. So really the personal air monitoring is an understanding of how much your work has been exposed to a particular air contaminant. And if the personal air monitoring is done well, then you can also understand what processes or products are the actual source of the exposure. And in the end, what we're looking at is to see whether or not the control measures that you've got in place currently are actually effective, or do you need to put something else in place? So we've got a picture there on the right-hand side of our respirable. Well, it's a respirable cyclone. So the respirable cyclone, this one's an SKC one, so it looks like this. What happens is the air goes up underneath in through there, it spins around in a cyclone. The large size particles drop away. We don't analyse those, and the rest of it sticks up underneath. Where are we? Underneath on a filter which is within there, and that connects to the pump. So the air goes up, spins around, contaminants sit on the filter we send for analysis, and then the air just goes through the pump because that's a vacuum pump. So that's how we actually sample for respirable crystalline silica. So what happens is only the smallest size particles, so the respirable size particles, are the ones that are on the filter. As I suggested, the bigger size, which would be part of the inhalable dust size, which we're not interested in for silica, falls down through the bottom. So we've only got the size which is going to go right down to the alveoli. So it's there is a method, Australian Standard 2985 for workplace exposures method for sampling and gravimetric determination of respirable dust. So there's actually methodology which has been standardised for the measurement, sampling and measurement for respirable crystalline silica. We talk about personal air monitoring, as I suggested, and that's where we have the sample head up in the breathing zone of the worker. So that's within a 1 foot or a 30 centimetre sphere around the face. And that's where people go and stick their head. That's where we want to be sampling from. So the other thing that we look at is that our samples need to be tested by a National Association of Testing Authorities accredited lab, so that's a NATA lab. So we have good QA, QC processes going on, and everything can be replicated again. So the types of monitoring that we do can stand up the rigours of investigation, and that could be a court process potentially. So personal air monitoring, again, you can see that that's that cyclone, respirable size fraction cyclone in through there. The tubing attaches to that pump. This is an old pump that's quite a big one, but the pumps come in various sizes, shapes, forms these days. We talk about the pumps must have very specific capabilities, and those capabilities would be that it needs to have the capability of running at a smooth flow rate of 3 litres per minute plus or minus 0.1. So that's your 5% error margin in through there throughout the entire sampling period. And we need to make sure that we calibrate the pump before and after use to make sure that it's actually working the way it ought to. This is where that flow rate variance in through there, that 5% variance comes in. So there's a bit of, like I said, there's rigor involved with the methodology as to how we do the monitoring. And we like to make sure we get sampling done for the whole of the shift. So the whole of the time that a person might be exposed to an airborne contaminant, we'd like to be sampling for all of that period of time, so we get a representative example of someone's work exposure. All right, health monitoring. So in the end, health monitoring is after the event. So under the WorkSafe Australia guidelines, health monitoring is required for all workers that are exposed to crystalline silica. Health monitoring is aimed primarily at identifying the effects of workplace exposure to hazardous chemicals, and the health monitoring does not include air monitoring or other measures to assess or control exposure to hazardous chemicals in the workplace. So that the air monitoring itself has got nothing to do with the actual health monitoring. The health monitoring is what we call biological monitoring. So that's how your body has the body burden of the exposure and whether or not there's actually a health effect beginning. So things that we're looking at with our health monitoring or our biological monitoring. So again, you've already been exposed. So therefore, we're looking to see whether or not there has been a health effect or there is a health effect. So the idea of the health monitoring is that it should never be used as an alternative to putting in place actual effective health, exposure control measures, because the health monitoring is meant to be after your exposure, so it's too late. So typical testing could be records of personal exposure, physical examination. It could be a standardised respiratory questionnaire as well, and then you start getting into the diagnostic sort of field, and that where you're looking at lung function tests like spirometry, and then we've got a picture of someone busy blowing into a spirometer there, and then a chest x-ray. The chest x-ray can only show you changes which are already there, and you can't do anything about them by the time it's actually visible on a chest x-ray. You can get a bit of an indication for the lung function test and the spirometry of decreased lung function, which might need further investigation, but by the time you can see it on an x-ray, that's bad news. So just to reiterate, by the time you can see it, someone's already been exposed, and for silicosis, there is no cure. So doing health monitoring is not a control measure. The health monitoring is a measure of whether or not your controls are adequate. Right, so come on. Here we go. So dust controls. How do we control exposure? Those of us who work, have been around a little bit, are particularly familiar with the, sorry, just trying to get it back. Very touchy, these slides. Here we go, the hierarchy of controls. So the idea is, let's eliminate or remove the hazard so that people aren't exposed in the first place. And then there you go down through to substitution, so change to a safer alternative. So we might remove silica-based or silica percentage or of a particular product we might be using, and change it to a lower percentage silica content, or that's probably the best way that we would be looking at a control for there. Separation and isolation. So separate people from the dust with a barrier or distance, or maybe time. So you rotate people through tasks as well. You might have a, let's say, a sandblasting booth, separates other people from that particular contaminant. You might be looking at engineering controls. So you might redesign and modify tools and equipment. So you might have dust extraction actually on your tool or within the workplace. You might have other administration controls, like making sure people get trained in the use of all of those, all of the other higher order controls, and then goes right down to the bottom end, the pointy end, where the only barrier that's left is personal protective equipment, and that would be most specifically respiratory protection in the case of the hazard being respirable crystalline silica. So let's have a look. There's a bit of legislation stuff in through here, and we talk about employers or PCBUs needing to apply the hierarchy of controls as per the requirements of the relevant legislation. And the terminology is usually got to do with eliminating all risks so far as reasonably practicable. If an elimination is not reasonably practicable, then risk must be minimised so far as reasonably practicable. It means if you know something's going on, you need to do a risk assessment. You need to put some controls in place to protect your workers as best as possible. And as best as possible, or reasonably practicable, is best practice. Best practice wins. Even though you might have legislation, you might adhere to the current legislation. Best practice still wins if there's something which can be done better, and you don't do it. Even though you're abiding by your legislation, that still might put you liable. Okay, so controls. I'm not very comfortable with this particular slide. It doesn't represent it very well, but if we're looking in through here, controls, we as hygienists like to look at control at the source. So where that hazard is, we want to try and control the source. And the prevention activities are in there: elimination, substitution, isolation, engineering. Once that source or the hazard becomes airborne, so the respirable crystalline silica then becomes airborne, that transmission pathway then goes into the right-hand side here of protection to the worker or the receiver. So that's where you've got administration and PPE types of things in through there. And if they are not working effectively, along with a reduction of the amount of material that might be made airborne, then you'll have an exposure, and then there's likely health effects after that. So there are a whole range of controlled examples. We've got certainly within quarrying and the mining environment, you've got roadway dust suppression activities by using water trucks, for example. You can use just water itself, or we sometimes have additives in through there like surfactants and polymer films, sometimes bituminous products in through there to try and keep the dust levels down. If we're looking in a travel way on a mine site, for example, we might increase the distance between trucks to allow the dust to settle, reduce speed levels, travel only on the marked roads, so the ones that are actually being monitored and conditioned appropriately. Other things that we might have in through here, this is, like I said, fairly mining / quarry centric, but within machinery, heavy mobile equipment, within the cabins, we have controls in there like enclosed cabins, and it might have cabin pressure monitors in through there, and that's what we've got on the right hand side there. You can see that there's a cabin pressure meter in through there, and you can have a look at it and see whether or not the cabin has got a positive pressure in there, which would force any dust out. So you need to have a positive pressure within your cab. Hopefully, yeah, here we go. So the cabin pressure is tested, or the seals in the cabins would be bombed or gas bombed with small smoke test to check the seals. And as I suggested that last slide, you might have a pressure gauge to identify that you've definitely got a positive pressure in through your cab. Other types of controls might be a windows up policy, so that's a administration control. So anything less than an engineering control relies on people's behaviours. So administration controls and PPE controls is all behaviour related, and you hope that people are trained appropriately to be able to use controls in place. But if you're only relying on people's behaviours, then they're obviously a low level control. Vacuuming cabins regularly to reduce dust buildup within the cabin, so that could be just from people's mud on people's feet, for example. And how do you actually clean within the cab of a heavy mobile equipment? You don't use compressed air, for example, because it'll just increase the dust levels. Okay, so if we go down through into respiratory protection, so what we talk about with respiratory protection is compliance with the Australian Standard 1715, and to ensure the adequate protection is there when workers use a respirator. We need to make sure they've got an effective seal on that on that respirator. So that's where we call the very early slide, which had the depiction of the size of the particles that we're trying to exclude from our airway and the size of human hair. So you need to be clean shaven or only have facial hair that doesn't interfere with the seal of the mask. And you need to be fit tested as well. That's called up in the Australian standard 1715 as well, the fit testing. So that 1715 Australian standard is the selection, use and maintenance of respiratory protective equipment. Let's have a look, come on down. I knew it was going to do that. So, yep, there we go. So respiratory fit testing, what we've got on the right-hand side there, and the picture in through there is actually of one of our employees with what we call qualitative fit testing. So qualitative fit testing, mask fit testing, is a pass or fail type of method where workers assess whether or not they could smell or taste a variety of different chemicals to determine whether or not the mask that they're wearing is actually leaking. And quantitative uses specialised equipment like a porta count unit to measure how many particles are actually inside the mask and how much is outside the mask to make sure whether or not there's a leakage. So what we like to do as hygienists, we like numbers. You can stand up in court with numbers, and you cannot with qualitative. So qualitative, we say is I reckon that mask is working because the person says that they can't smell or taste that particular chemical that they've been exposed to for the test. However, there's limitations there because some people can't smell or taste it anyway, and it doesn't give you how much protection that particular mask is giving you. There's a whole range of problems with that qualitative form of fit testing. So we would support quantitative, where you're measuring actually how many particles are inside the mask and how much is outside the mask to make sure that you've got an appropriate fit. So I think we flew through that. So really, that's the end of my part, unless there's some questions to field.
Thank you very much, Simon, for your presentation today. So if anyone does have any other questions for Simon, please use your control panel to type and submit those questions. So Simon, you spoke about dust and roads. A further question has come through in respect to the following, which are likely to generate RCS: dry cutting clay bricks, dry cutting bitumen, dry cutting concrete, civil construction road base.
Oh, I haven't actually done specific monitoring on those three activities to have proof. I would say that if you think about the content of silica within the materials that you're thinking about, so you've got your cement products. They tend to have a higher respirable crystalline silica content, and your clay bricks as well. Certainly the bitumised road, potentially not so much, because it's more likely with the bitumen, as the product of bitumen being as sticky as it is, and that's why we use it for what we use it for, is more likely, in my opinion, to probably bind the respirable crystalline silica into a size of particle which is less likely to be inhaled. Inhaled down into the small parts of your lung, which are going to cause the issue. But like I said, I haven't actually had very specific monitoring data to have a really informed opinion of that. It's really just a conjecture. I'm pretty sure that the clay bricks and the concrete are definitely the ones that are going to be the ones causing most issue.
Thanks. From a compensation perspective, can silicosis be differentiated from asbestos or smoking-induced cancers?
I believe that this is a little bit outside of my realm. That's more for an occupational physician or a respiratory physician to actually make that judgment call. But certainly asbestos-related diseases, there are two very specific asbestos-related diseases, and that is asbestosis and mesothelioma, that are you can only get them from exposure to asbestos, but you can get lung cancers from asbestos as well. So I don't know how they would differentiate between a lung cancer specifically caused by asbestos as opposed to any other product. And the same goes with silica. Silicosis is a very specific silica-related silica exposure-related disease, whereas lung cancers can be caused by numerous mechanisms. So that's a sneaky question, and that's outside of my jurisdiction, if you like. But I would say if you had silicosis, you had silicon exposure. And if you have lung cancer, then it might be combined with other exposures of various contaminants through your personal or your work environment.
Thanks, Simon. Type H vacuums are extremely expensive to purchase and service, considering they have such a marginal filtration to class M, 0.095%. Did you want to comment on that comment?
Yeah, that's a fantastic question. I don't work with those vacuum cleaners specifically. I don't actually. We would mostly be using those in the asbestos removal field, but my understanding is the H-type vacuum cleaners are the HEPA filter vacuum cleaners. I pinched that knowledge from a slide from one of my colleagues, so I don't have the same amount of knowledge as he does. So that's as good as my answer gets. Sorry.
Okay. Are you also just able to repeat where people can get general information on silica in the atmosphere and exposure?
Sure. The WorkSafe Australia is probably the best place to go to look at their materials that they have online. All of their materials are free, and they can sometimes point you in the direction of other material that might be useful within your state health and safety groups. So that, it could be WorkSafe Tasmania, for example, it could be WorkSafe WA, it could be New South Wales, it could be Queensland. So I think the first port of call should be the federal WorkSafe Australia, and go from there. The other opportunity would be, of course, to contact a reputable hygienist or organisation who can help you with that, and that would be, I'd point you in the right direction there, and that would be go via the AIOH. So that's the Australian Institute of Occupational Hygienists. They can point you towards the right type of consultant that can help you out further if you think that you need some further specialist advice.
Thank you very much, Simon. So we'll now close today's webinar with no further questions coming through. So thank you to today's presenter, Simon Sharp, Contractor, to the Institute of Quarrying Australia, and thank you to everyone for attending today's webinar, which is part of WorkSafe Tasmania Month. WorkSafe Month runs throughout the month of October. Please head to worksafe.tas.gov.au to find out what's happening in Tasmania. To find out what's happening Australia-wide, please head to the Safe Work Australia website. WorkSafe Tasmania Month is an initiative funded by the WorkCover Tasmania Board, delivered by WorkSafe Tasmania. So thank you everyone for attending today.
Thank you.